So last time we stated what is Wick's theorem. So in this lecture we will try to prove Wick's theorem. So before we went on to prove the Wick's theorem, let's do our first few simple cases to get the general how to go ahead and do the most general case. So in the previous lecture we introduced the notion of contraction. So let's start with the simple case. So the simplest case of Wick theorem is, let's say there is only one operator. I mean, in that case the left hand side and the right hand side, in that case the left hand side and the right hand side are same. So there is nothing to show in the case for only one of them. Now we already have also done two of them, so let's start with that. This is same as we have shown it already. Plus this. So in this lecture we will try to do this first explicitly for three of them. Okay, so in order to do that, let's say we have this. Okay, now for these two, I can just use the result from the above result, right? So these two is simply phi I t1 plus so this part is automatically good. There is nothing there is nothing more you can do about it. We have to focus on this part. Good. In order to evaluate that, let's first write phi I t. This is equal to where phi I plus t is same as h bar power 2m a dagger minus not minus imt and phi I minus is okay. Now let's put this expression here. So we get two terms. We get phi I plus phi 1 phi I plus T1 phi I T2 phi I T3, and I have phi I minus T1 phi I T2 phi I T3. Now this term, okay, this is already normal ordered. Why? Because phi plus has only creation operator, and it is at the rightmost position. Then also note that anything left to it is also normal ordered by our construction. So the whole thing is normal ordered. So this thing is normal ordered. So we are good with this term. Now our worry is how to do this term. Okay. So what we have to do, we have to, since this has one annihilation operator, this has one annihilation operator, and each of them have one creation operator, right? This means that we have to convert it to something like this. We have to do something like this. We have to bring it to the rightmost position. So how do we do that? Then we write this quantity in terms of commutators. So we write it as T1 commutator plus phi I T2 phi minus T1 commutator phi I plus phi I Okay, so this term is already good again. This term is good. Because this is already normal order, this is what we want. So what about the other two terms? Now it is this is not very difficult to do, that phi I minus T1 phi I T2, this will simply become phi I minus T1 with phi I plus T2 plus phi I minus T1 phi I minus T2. Okay. Now this term is automatically 0. This term is 0 because both has annihilation operators. What about this term? So this term is simply the commutator of A with A dagger exponential minus I m T1 plus I m T2. Okay, so this is, then this term is simply same as this d greater T1 minus T2. Okay, so we evaluated this quantity. This is this. In the same way, we can also evaluate this quantity. So what we get altogether? So altogether we have how many terms? So we have this. So we have this. We have this. We have this, and we also have to collect one term from here, somewhere here. Here. Okay. So let's write everything together. So let's first write this term. Plus, so if I put it here, so here will be propagator. So one term will have T3. One has the Whiteman propagator between 1 and 2, and then phi I T3. Similarly here I have phi I T2 and Whiteman propagator. So here I have phi I T2 and Whiteman propagator between T1 and T3. And the term that we left on top here, this term is phi I T1 T2 minus T3. So we see that this is precisely the Wick theorem for 3 operators. So this is the Okay, great. So now how we go ahead and prove it for more general, any number of operators. So let's say I have n number of operators. N plus 1, let's say. Now you see we have already proven for we explicitly have proven for n equal to 0, 1 and 2. Okay. So let's now try to do it in the inductive way. So let's assume, let's say Wick's theorem is true for some integer n greater than 3, okay, because up to greater than equal to 3 we have proved up to 2, and we will try to prove it for n equals 1. Okay, so let's do it. Okay, so step 1, use the result, use the theorem for n, which means that for this part we assume it to be true. Okay, so for this part then we can write it as plus all possible single contraction yes, all possible double contraction dot after this. Okay, so now let's introduce a bit of a notation. So let's light W n comma m phi I1 dot 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 phi I n minus 2m phi I n minus 2m plus 1 phi I n minus 2m plus 2 dot dot dot. Okay, so this notation means that, so this means there are n fields they are normal ordered and two of them are contracted okay. Now your question will be which 2m are contracted. So the 2m are contracted is phi I n minus 2m plus 1 is contracted with phi I n minus 2m plus 2 and likewise. So let's give an example. Let's say I have w3 2 phi 1 and let's say phi 2 phi 1 phi 3. I mean phi 1 means phi, okay, so so this should have been careful. So this is phi 2 means phi at time t2 and this means phi at time t1 and this is phi 3. Okay, this means this quantity is same as phi 2. We will always write in this way, phi 1 phi 2 dot 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 phi 3 and these two are contracted. So this notation means that. Okay, so now you see that this is basically, this thing is wn0 phi t2 to phi tn plus 1 and this quantity is phi n1 and likewise. Okay, so this is the notation. So what we have got, so after using an inductive hypothesis, we have got phi t1 and then we have wn0 and then we have sum over wn1 because there are many type of single contractions. Then I have these are capital N, wn2 plus dot dot dot. Now second step is that we write this thing in terms of, so step 2. We write phi t1 in terms of phi plus t1 plus phi minus t1. Okay, so second step is to write in terms of phi plus t1 and phi minus t1 and then when we put it back, phi plus t1 multiplying this is already normal ordered. Okay, so we have to worry, step 3, we have to worry about phi minus T1 okay. Now let's consider in any phi minus T1 times some W n comma m, okay, where m is an arbitrary, so here m is greater than equal to 0, less than equal to the greatest integer less than n by 2. So once I look at these things, so this quantity is phi I minus T1, and then you have phi T2 dot 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 Tn plus 1, and then you have m contraction, some m, something like that, some m contractions. And actually you have to consider all possible such m contractions. So now what is the strategy? The strategy is that we have to bring it to leftmost position, rightmost position. We have to bring it to rightmost position. How do we do that? So bring commutators, simply the same strategy as above. So if I do that, the end result will be of course phi T2 dot 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 Tn plus 1, Tn plus 1 and phi minus T1, and then plus you have this quantity here, for example phi minus T1 commutator with phi T2 dot dot dot, and so and more such terms. Now all of this will simply give you this Whiteman propagators. We have shown it. So then what we will get? So what we will get is that let's look at this term. Wn comma m. So this has n fields, phi T2 to phi Tn plus 1. M are contracted. Okay. Now once we do this, so we will see two types of things. So one type of thing is this term. So this type of term, they belong to Wn plus 1 m, right? Because there are m fields now, n plus 1 fields now, but only m of them are still contracted, right? And then you have this kind of fields where you again have Wn plus 1, you have still have n plus 1 fields, but m plus 1 of them are contracted. Okay, so from this we get Wn plus 1 m. There are two very particular types. I will come to this. So in this part, though this is Wn plus 1 m, only phi 2 to phi n plus 1 can be contracted here. And this is, though there is n plus 1, here phi 1 is necessarily contracted. Okay, because we saw that this is commutative. So this is the thing we kind of get. But then if we look at other kind of terms, for example, if I look at phi minus m plus 1, this will give the other, this will complete this set. Okay, so let's write in this way. So in the Wn plus 1 m, this can be written as two ways: W hat n plus 1 m and W tilde n plus 1 m. By that I mean that though this is m field contracted, phi 1 is always contracted. And this you get where phi 1 is not contracted. And of course all permutation for others. So then from this we can see that these thing, so this is simply W tilde, because here phi 2 is never not at all contracted, phi 1, and this is simply W hat. Simply from here, if I start from here, I will get W tilde I will get W tilde n plus 1 comma m plus 1, and then I will also get W hat n plus 1 comma m plus 2. So in this way I can add this two to get all possible W n plus 1 comma m plus 1. Okay, so this is the way we will I mean, if you just complete these steps, then it will this will be the proof of Wick's theorem. Okay, so it will be clearly written in the note, and you can refer to the note and check how it is done, and this will basically complete the proof of the Wick's theorem. Okay, in the next lecture we will see that how can we use Wick's theorem to do interesting things.